안녕하십니까? 제가 정찬수입니다. 한국말은 잘 못하니까 죄송합니다. 그래서 발표 영어로 하겠습니다. So a month ago, when I submitted a proposal to present here, I was going to talk just about industry-scale chemistry simulation before fault tolerance. And 10 days ago, IBM Quantum released our plan to fault tolerance. And so I wanted to also tell you about our plan. So I have 15 minutes. So I encourage you to please come by our booth and learn more. So at a high level, this is what we plan the next 4 years. First step, this year, we will demonstrate a quantum-centric supercomputer, and I'll show you some pictures of that. Next year, we plan to demonstrate quantum advantage. This will require the quantum computing communities and the high-performance computing communities to work together. In 2027, we expect to demonstrate a viable path to error-corrected quantum computers. And finally, in 2028, we'll demonstrate the first error-corrected quantum computer. Okay, so this is the plan. Again, there's a lot of detail here. I encourage you to come by our booth because I only have 15 minutes to tell you about all of these 4 things. Okay, so let's start. So when we talk about a quantum-centric supercomputer, we don't mean a large quantum computer. What we mean is combining the best of a quantum computer, a supercomputer, and a GPU all together to create something bigger, something better. We have already built 2 of these. The first one was established last year at Rensselaer Polytechnic Institute, a university in New York State in the United States. And then just this morning, we announced this system. It's the first IBM Quantum System 2 outside the United States. It is built at the Riken Supercomputer Center in Japan. Now, what will we run on these machines? Well, an interesting problem to solve is developing new materials. The largest jumps in product cost performance comes from new materials. And let me give you one example. There are many examples, but let me give you one. This is work that we did with Mitsubishi Chemical in simulating batteries. You can see that most batteries have a relatively low energy density compared to gasoline. Gasoline is 10 to 100 times larger than most battery chemistries. However, there is one battery chemistry that has an energy density that is comparable to gasoline, and that is the lithium-air battery. This battery is still in development, but one of the things we did together with Mitsubishi Chemical is we simulated this on a quantum computer. This is still now several years old, but you can see that this orange line is the exact solution, and the red and green lines are the outputs from our quantum computers. You can see already we were getting pretty close a couple of years ago, and now our methods are much more advanced, and I expect that we would be much more accurate. But the point is that by simulating this battery, we can help develop the lithium-air battery, which has a high energy density comparable to that of gasoline. Now, the problem is it takes a long time to develop new materials. 10 to 20 years is very typical. My experience, more like 40 years is a development time. And the primary reason is because unlike most areas of engineering and science, materials development is still not a computational discipline. It is still largely an empirical discipline. Most of the learning happens through empirical trial and error methods. In other words, you try something and you fail, and you try something and you fail, and it's a very slow process, and that's why the development time is on the order of decades and not years. One of the reasons why this has remained an empirical discipline is because a lot of computational simulation techniques don't work very well. So if there was a computational way to do these trial and errors rather than doing them experimentally, this could be much faster. Instead of a 10 to 20-year development time, we could imagine a 1 to 2 year development time. So last year, we presented this algorithm called the sampling-based quantum diagonalization algorithm, SQD. We simulated this molecule. This is a complex molecule to simulate because it includes iron, a transition metal. You can see our solutions here. What we're looking at here is what's called the electronic structure of the molecule. You can see 3 solutions in these straight lines here. This third line is the ground state, and what you're seeing here is a confirmation that the solution is accurate by the most advanced classical algorithm. So this is what happened last year. This past year, what we have demonstrated is we've essentially been stress testing the SQD algorithm. So the first thing is we developed was we demonstrated it for transition metal molecules. We have since then demonstrated it for excited states. We've now done it for open shell systems. And between these two, we have now demonstrated that excited states is a multi-reference situation. Open shell systems are high entanglement situations. We've kind of demonstrated the 2 areas that have great difficulty in computational simulation. Since then, the Cleveland Clinic has also demonstrated SQD for other kinds of interactions, these hydrogen bonds that occurs between biological molecules, solvent-solute reactions, and finally an embedding technique so that one can use SQD for larger and larger molecules. So this is what happened last year. Next year, we're planning on extending SQD to demonstrate quantum advantage, and so stay tuned for that. We've also been able to integrate SQD so that you don't have to write the code yourself. It is now part of our Qiskit software development platform, and you can simply log into Qiskit and you can use SQD as a standalone subroutine. To give you a sense of how quickly this came about, with 1 year of research, we developed SQD with Riken, and then the Cleveland Clinic and Lockheed Martin used about 3 months in order to leverage that for the papers that I showed you before. Okay, so that's in the past. Let's look towards the future. This is our roadmap looking forward. There is a lot of detail here. Let me orient you a little bit here. So this top part, this is our roadmap that will be client-facing. These are all systems that that you will be able to use. The roadmap down here is our innovation roadmap, and these are internal milestones for IBM that allow us to deliver the things that you see up in the development roadmap. Let me point out a couple of highlights on the development roadmap. We are here in 2025. We plan to offer, we already have the Heron quantum processor available now. It is running 5,000 or executing 5,000 2-qubit gates in a way that is meaningful. You can get accurate answers out of this, and this is the most in the world. Looking forward, later this year, we'll be delivering the Nighthawk QPU. It will have 120 qubits, and we'll have a different connectivity. It will have a square lattice connectivity. And then what we plan to do is increase the number of 2-qubit gates that you can execute from there. We'll go to 7,500 qubits next year, 10,000 qubits the following year, and 15,000 qubits in 2028. These layers you can kind of think of as, so if this is the hardware layer, you can think of this as some kind of a software layer. This is a software layer for combining quantum computers with high-performance classical computers. You can also think of this as an algorithm layer, and finally you can think of this as an applications layer. Now, another thing to point out is in 2029, the number of 2-qubit gates we'll be able to execute jumps from 15,000 to 100 million. So what is going on there, you can see down in our innovation roadmap here. And let me give you a summary in this slide. So this year we'll be demonstrating Loon. Loon will be essentially demonstrating fault-tolerant memory, so quantum error-corrected memory. We'll be demonstrating 2 logical qubits this year. In 2026, we'll be demonstrating a system called Kookaburra. It adds this component. This is essentially a way to apply logical operations to memory. So it's not enough to have simply quantum error-corrected memory. You also have to have quantum error-corrected memory as well as operations. So we'll be demonstrating both of those next year. In 2027, we'll be demonstrating the Cockatoo system. This will essentially be combining 2 Kookaburra systems together connected by this quantum connection. What this shows is a scalable method to grow and build a larger quantum computer, which will be the basis for us to deliver Starling in 2028. Starling will have a 200 logical qubit system capable of executing 100 million 100 million 2-qubit gates. And the system will look something like this. So this is our quantum system 2s. These will be the systems that will deliver, will execute SQD, and will be delivering, demonstrating quantum advantage in 2026. This is the Starling system that will have 200 logical qubits and 100 million 2-qubit gates. And then this is finally our Blue Jay system. We plan to deliver this in 2033. It will have 2,000 logical qubits as well as 1 billion quantum gates. Okay. As I said, there's a lot of information. There's a lot of detail. I encourage you to come to our booth and learn more about our plans to deliver a quantum error-corrected computer, but also to realize quantum advantage before we do that. Thank you very much.